Across the vast, silent expanse of the universe, something truly extraordinary is happening right now. A star, many times more massive than our own sun, is nearing the end of its life. For millions of years, it has burned with incredible ferocity, forging heavier and heavier elements deep within its core. It has been a beacon of light and energy in its corner of the galaxy, a celestial powerhouse that has lived a brilliant and turbulent existence. But now its fuel is running out. The delicate balance between the inward crush of gravity and the outward push of nuclear fusion is about to be catastrophically broken. The star is poised on the brink of an unimaginably violent death, a final, breathtaking act that will briefly outshine its entire galaxy. This event is called a supernova. It is one of the most powerful and spectacular phenomena the universe has to offer. In a mere fraction of a second, the star's core will collapse under its own immense weight, triggering an explosion of such magnitude that it defies everyday comprehension. The energy released is simply staggering, sending a shockwave of matter and radiation hurtling outwards into space at incredible speeds. Imagine trying to photograph a flash of lightning. You know it will happen during a storm, but you don't know precisely where or when the next bolt will strike. Now imagine that storm is an entire galaxy, and the lightning flash lasts for mere moments, but you have to wait 100 years for it to happen. That gives you some idea of the immense challenge astronomers face when trying to observe a supernova. For most of history, we have been cosmic archaeologists, studying the aftermath of these explosions long after the main event has finished. We see the beautiful, expanding clouds of gas and dust, the supernova remnants, but we miss the most crucial part, the explosion itself. To truly understand what happens in the final, frantic seconds of a star's life, we need to see the core collapse as it happens. We need to witness the cataclysm unfolding in real time. The problem is that the core, the very heart of the action, is shrouded from our view. It is buried deep within the star's own thick outer layers of gas. By the time the brilliant flash of light from the explosion punches its way out of the star and begins its long journey across space to our telescopes, the critical first moments are already over. We need a witness, a messenger that can escape the collapsing star's core instantly and travel unimpeded across the vastness of space to tell us that a star is about to die. So what exactly is this mysterious particle, the neutrino? To understand it, we must journey into the strange and wonderful world of the very small, the realm of subatomic physics. Everything around us, from the stars in the sky to the ground beneath our feet, is made of fundamental particles. The neutrino is another one of these fundamental building blocks of reality, but it is a very peculiar one. It has no electric charge, which means it is not pushed or pulled by electromagnetic forces, the forces that hold atoms together and govern light itself. The neutrino is also incredibly light. For a long time, we thought it had no mass at all. We now know it has a tiny amount, but it is almost immeasurably small, millions of times lighter than even a single electron. This combination of having no charge and virtually no mass is what makes the neutrino so elusive, so ghostly. It is the ultimate cosmic introvert, a particle that barely acknowledges the existence of the rest of the universe. The idea of the neutrino was first proposed in 1930 by the brilliant physicist Wolfgang Pauli. He was trying to solve a puzzle in nuclear physics concerning a process called beta decay. The problem was that the energy before and after the decay did not seem to add up. Some energy was always missing. Rather than accept that the fundamental law of conservation of energy was wrong, Pauli made a bold suggestion. He proposed that another unseen particle was being created in the decay, a particle that was carrying away the missing energy. He jokingly called it a desperate remedy, but he was right. It took another 26 years before Pauli's hypothetical particle was finally detected, confirming its existence. The experiment that found it was a monumental feat, a testament to how difficult it is to catch a neutrino. To truly appreciate the neutrino's unique ability, let's consider its journey compared to that of light. Light, or a photon, is also a fundamental particle, but it interacts very readily with matter. As light from the sun's core begins its journey outwards, it is immediately absorbed by an atom, then re-emitted in a random direction, only to be absorbed by another atom moments later. It staggers around inside the sun like a drunken man trying to find his way out of a crowded room. This random walk means that it can take hundreds of thousands of years for the energy created in the sun's core to finally reach the surface. Now consider a neutrino born in the same nuclear reaction deep inside the sun's core. It feels no electromagnetic force, and its tiny mass means it is barely affected by gravity. The dense hot plasma of the solar interior, an impenetrable wall for a photon of light, is no obstacle at all for the neutrino. It flies straight out, unimpeded. It travels from the very center of the sun to its surface in just over 2 seconds, and from there it continues its journey across the solar system at very nearly the speed of light, reaching Earth in about 8 minutes. It is an almost instantaneous messenger, carrying direct information from the heart of a star. This incredible ability to pass through matter is what allows neutrinos to escape the heart of a supernova. When a massive star's core collapses, it becomes one of the densest places in the universe. The immense burst of energy from the collapse creates a flood of them, an unimaginable number, more than all the stars in the observable universe produce in a single moment. While the shockwave and the light are still fighting their way out from the star's core, the neutrinos have already gone. They are the first heralds of the star's death, an advance party carrying the news of the explosion. Neutrinos are not just created in the sun or in distant supernovae. They are being produced all around us all the time. They are a natural part of the universe. Some were created in the Big Bang itself, and these ancient relics still roam the cosmos today, a faint echo of creation. Others are produced in our planet's own atmosphere, when high-energy cosmic rays from space smash into air molecules. However, the neutrinos that interest us as supernova hunters are the high-energy ones, those forged in the most violent cosmic events. A supernova explosion is, by a huge margin, the most powerful neutrino source we know of. In just 10 seconds, a single core collapse supernova releases more energy in the form of neutrinos than our own sun will radiate in its entire 10 billion year lifetime. It is a truly mind-boggling amount of energy, all carried away by these tiny, ghostly particles. To understand why a supernova creates such a staggering number of neutrinos, we have to look deep inside the heart of a truly massive star as it dies. For millions of years, the star has been a magnificent nuclear furnace. It starts by fusing hydrogen into helium, just like our sun. But because it is so much more massive, its core is hotter and denser. It burns through its fuel much faster, moving on to fuse helium into carbon, then carbon into neon, oxygen, silicon, and finally iron. The creation of an iron core signals the beginning of the end. Iron is a kind of nuclear ash. Fusing iron atoms together does not release energy, it consumes it. The star has reached a dead end. With its energy source shut off, there is nothing left to support the colossal weight of its outer layers. In less than a second, gravity wins the long war. The iron core, a ball of matter about the size of the Earth but with the mass of our sun, collapses catastrophically. Protons and electrons, the fundamental components of atoms, are crushed together with unimaginable force. They merge to form neutrons, and in this process a single neutrino is released for every neutron created. This process, known as neutronization, unleashes a torrent of neutrinos. We have established that the supernova explosion creates two main things: a brilliant flash of light and an incomprehensible flood of neutrinos. Both begin their journey from the same event, deep inside the star's core. But they do not emerge from the star at the same time. The neutrinos, as we have learned, barely interact with matter. As soon as they are created in the collapsing core, they are free. They stream out of the star almost instantly, flying through the dense outer layers of gas as if they were not even there. The light, however, has a much tougher time. The light is generated by the colossal shockwave as it smashes its way outwards from the core. This shockwave is incredibly powerful, but it is moving through an incredibly dense medium, the star's own body. This difference in escape time creates a vital window of opportunity for us here on Earth. The neutrinos arrive first. They are the advance warning system, the cosmic Paul Revere, riding ahead to announce that the explosion is coming. Depending on the star, they can give us a head start of several hours. Imagine receiving a text message telling you exactly where and when a magnificent firework is about to launch, hours before it actually happens. You would have time to grab your camera, find the perfect viewing spot, and point your lens in the right direction, ready to capture the spectacle the moment it begins. This is precisely what neutrinos offer to astronomers. So, we know that a supernova sends a colossal flood of neutrinos hurtling towards us. We also know that these particles are incredibly difficult to catch. So how on earth do we build a trap for a ghost? The answer is a fascinating blend of massive scale and delicate sensitivity. It involves building detectors so enormous that they increase the vanishingly small probability of a neutrino interaction to a level we can actually measure. To have any hope of seeing the faint signal from a neutrino interaction, you have to eliminate all other sources of noise. This means the detectors must be built deep underground. The Earth itself is used as a giant shield. One of the most famous and successful neutrino detectors in the world is Super-Kamiokande, or Super-K for short. Located deep inside Mount Ikino in Japan, it is a truly breathtaking scientific instrument. To reach it, you have to drive down a long tunnel into the heart of an old zinc mine. There, in a vast excavated cavern, sits a colossal stainless steel tank, 40 meters tall and 40 meters wide. It is large enough to comfortably house the Statue of Liberty. This gigantic tank is filled with 50,000 tons of ultra-pure water, a volume so vast it would take months to fill from a normal tap. The inside of this immense tank is lined with more than 13,000 golden-hued photomultiplier tubes, each one half a meter in diameter. They point inwards, staring into the silent dark water, waiting for the telltale blue flash of Cherenkov light. When technicians need to service the PMTs, they drain the tank and navigate its interior in small rubber boats, floating in a cavernous space surrounded by a honeycomb of thousands of giant, golden eyes. When a high-energy neutrino from a supernova zips into the tank, it might strike the nucleus of an oxygen atom or a proton in a water molecule. This collision produces other faster-moving charged particles, creating a shock wave of light, a phenomenon known as Cherenkov radiation. Super-Kamiokande is constantly watching, 24 hours a day, 7 days a week. It is one of the key instruments in the global network designed to spot supernova neutrinos. The detector is part of an early warning system called the Supernova Neutrino Early Warning System, or SNEWS. The computers at Super-K, along with those at other neutrino detectors around the world, are constantly looking for a sudden, sharp burst of neutrino events. If multiple detectors see the same signal, an automatic alert is sent out to astronomers across the globe in less than a minute. This is the starting gun. This is the message that tells the world's telescopes where to look, giving them hours to prepare for the arrival of the light from the explosion. While Super-Kamiokande uses a giant tank of water, another extraordinary experiment uses a different naturally occurring medium, the pristine, ultra-clear ice of Antarctica. This is the IceCube Neutrino Observatory, and it is arguably the strangest telescope in the world. Its detector is not a single tank in a mine, but a cubic kilometer of solid glacial ice located deep beneath the geographic South Pole. To build IceCube, an international team had to drill 86 incredibly deep holes into the ice, each one 2.5 kilometers deep. They used a custom-designed hot water drill to melt their way down into the ice sheet. Into these deep shafts, they lowered long strings of sensors like beads on a necklace. Each string holds 60 digital optical modules, which are essentially photomultiplier tubes and their control electronics encased in a protective glass sphere. In total, over 5,000 of these sensors are now frozen permanently in place, distributed throughout 1 billion tons of Antarctic ice. Just like in Super-K, IceCube's sensors are designed to detect the faint blue Cherenkov light produced when a high-energy neutrino interacts with an atom in the ice. The three-dimensional grid of sensors allows scientists to reconstruct the neutrino's path with incredible precision, effectively turning a cubic kilometer of the South Pole into the lens of a massive telescope, pointing out into the universe in all directions. It even uses the Earth itself as a filter, looking for neutrinos that have traveled all the way through the planet from the northern sky. For decades, this idea of detecting neutrinos from a supernova was purely theoretical. Scientists had calculated that it should be possible, and they had started building the giant detectors needed to do it, but they were waiting for a star to cooperate. Then, on the 23rd of February 1987, it happened. A star exploded in the large Magellanic Cloud, a small satellite galaxy orbiting our own Milky Way. It was the closest and brightest supernova seen in almost 400 years. It was named Supernova 1987A, and it would change astronomy forever. Before any telescope on Earth saw the new bright star in the sky, something incredible occurred. Deep underground in Japan, in a detector called Kamiokande 2, a handful of light sensors recorded a brief 12-second flash of activity. At almost the same instant, another detector in the United States, the Irvine, Michigan Brookhaven experiment, recorded a similar burst. Scientists at both facilities were initially puzzled, but when news of the supernova discovery broke a few hours later, they realized what they had seen. They had captured the ghost in the machine. They had detected the neutrinos from the collapsing core of the star. It was the first time in history this had ever been done. A total of just 25 neutrinos were detected from supernova 1987A across all the world's detectors. It might not sound like many, but it was a monumental scientific triumph. Those 24 fleeting particles confirmed decades of theoretical work. They proved that our models of how stars die were fundamentally correct. The detection of neutrinos from SN 1987A was the birth of neutrino astronomy. For centuries, astronomy has been a passive science. We have waited patiently for light from the cosmos to arrive at our telescopes, studying events that happened long ago. But the ability to detect neutrinos from a supernova in real time has changed everything. It has transformed us from passive observers into active participants. We no longer have to stumble upon the aftermath of a cosmic explosion by chance. Instead, we have an alarm bell, a cosmic telegram sent directly to us from the heart of a dying star. This system is not just a theoretical dream. It is a functioning global network that is standing watch right now, this very second. It is called the Supernova Early Warning System, or SNEWS. Once the snooze alert goes out, a frantic, coordinated race against time begins across the globe. The message is received in the control rooms of the world's greatest observatories, from the high deserts of Chile to the volcanic peaks of Hawaii. Astronomers and telescope operators will immediately stop what they are doing. Their new target is the patch of sky pinpointed by the neutrino signal. Robotic telescopes will slew into position within seconds of receiving the alert. The hunt is on, and the entire astronomical community is mobilized. The first challenge is to find the star that is about to explode. With the target identified, large telescopes will wait for the arrival of the shock breakout, the moment the explosion's light first becomes visible. The true power of this new era in astronomy lies not just in detecting neutrinos, but in combining their message with information from other cosmic messengers. We are moving from listening to a single instrument to hearing an entire cosmic orchestra. When the next galactic supernova happens, we will not just observe it with neutrinos, we will see its light with our optical, radio, and X-ray telescopes. And crucially, we may also be able to feel the vibrations it sends through the very fabric of space-time in the form of gravitational waves. A supernova signal arriving in neutrinos, gravitational waves, and then light would give us a complete 360-degree view of the event. Each messenger tells a different part of the story, and together they create a richer, more detailed narrative. When we talk about a supernova happening in our galaxy, there is one star that immediately comes to mind: Betelgeuse. This famous red supergiant, which marks the shoulder of the constellation Orion, is one of the most prominent candidates for the next galactic supernova. It is a colossal star, nearing the end of its life, and it is relatively close, only about 550 light-years away. For astronomers, Betelgeuse is not just a beautiful star, it is a ticking time bomb. We do not know if it will explode tomorrow or in 100,000 years, but we know its end is coming. When it does, it will be a spectacle unlike any other. When Betelgeuse finally goes supernova, the neutrino burst will be unmistakable. Our detectors here on Earth will be flooded with thousands upon thousands of neutrino events, a signal so strong and clear it will be impossible to miss. The snooze alert will go out instantly. We will know with absolute certainty that Betelgeuse has collapsed. Yet when we look up at the sky, it will still be there, the familiar red point of light in Orion, looking completely unchanged. For a few hours, we will be keepers of a spectacular secret. We will know that a star has died, while the rest of the world sees it shining as it always has. This period of waiting will be one of the most exciting moments in the history of science. Then it will happen. A new star, brighter than anything else in the night sky except for the moon, will appear. It will be so bright that it will be easily visible during the day. For weeks, we will have two suns in our sky, a distant one by day, and a brilliant dying one by night. It will be a celestial event witnessed by every person on Earth, a profound reminder of our connection to the cosmos and the dynamic, violent universe we inhabit. The real-time observation of a supernova like Betelgeuse will revolutionize our understanding of stellar evolution. The combination of the detailed neutrino signal and the comprehensive observations of the light that follows will provide a complete end-to-end view of a star's death. The detection of neutrinos from a supernova is far more than just an early warning system. It is a revolutionary scientific tool. It allows us to perform what is, in effect, a live autopsy on a dying star from hundreds of light years away. For the first time, we can peer beyond the star's opaque outer layers and witness the cataclysmic events happening in the core, the true heart of the explosion. The light that our telescopes see tells us about the shockwave tearing the star apart, but the neutrinos tell us about the engine that powers that shockwave. They carry a detailed report, written in the language of particle physics, directly from the source of the cataclysm itself. By studying the properties of the neutrinos that arrive at our detectors, we can reconstruct a moment-by-moment picture of the core's collapse. At the heart of most core collapse supernovae, a new and extraordinary object is born from the ashes of the old star. As the core is crushed by gravity, the protons and electrons are squeezed together to form neutrons, creating a substance of incredible density. The collapse is finally halted when these neutrons are packed as tightly as the laws of physics will allow. This creates an ultra-dense sphere, perhaps only 20 kilometers in diameter but containing more mass than our Sun. This object is a neutron star. The 10-second-long burst of neutrinos is the birth announcement of this neutron star. The newly formed neutron star is incredibly hot, with a temperature of hundreds of billions of degrees. It cools down rapidly by radiating its energy away in the most efficient way possible, by emitting a colossal flood of neutrinos. In some cases, if the original star is massive enough, the collapse might not stop at a neutron star. Gravity might be so overwhelmingly strong that it crushes the neutron star itself out of existence, forming a black hole. This too would leave a unique signature in the neutrino signal. Instead of the gentle 10-second fade of a cooling neutron star, we would expect to see a sudden sharp cutoff in the neutrino emission, as the event horizon of the black hole forms, swallowing everything, including the neutrinos. The detection of such a signal would be the first time humanity has ever witnessed the birth of a black hole in real time. We stand at the dawn of a new age in our exploration of the cosmos. The future of this incredible field is brighter than ever. Around the world, the next generation of neutrino detectors is being planned and constructed. These new experiments will be even larger, more sensitive, and more sophisticated than the ones we have today. In Japan, the Super-Kamiokande detector is being built. It will be a direct successor to Super-K, but vastly bigger, holding 250,000 tons of ultra-pure water. In the United States, the Deep Underground Neutrino Experiment, or DUNE, will use enormous tanks of liquid argon to achieve unprecedented precision. These new cosmic watchtowers will be able to detect supernova neutrinos not just from our own galaxy, but from our galactic neighbors as well. This global network of new and improved detectors represents a profound commitment to understanding our universe. It is a testament to our enduring curiosity, the same curiosity that drove our ancestors to chart the stars and record the appearance of celestial visitors. We are building these subterranean cathedrals of science not because it is easy, but because it is hard. Because the secrets they will unlock are among the most fundamental in all of nature. We are patiently laying our ghost traps, making them bigger and better, so that we are ready for the next time a star in our cosmic backyard decides to end its life in a blaze of glory. When that next galactic supernova occurs, we will be ready. The signal will not be a mere handful of events, like the precious 25 neutrinos from 1987A. It will be a flood of thousands, perhaps tens of thousands of detections. This deluge of data will provide a high-definition movie of the star's final moments. We will see the core collapse, the shockwave form, and the neutron star ignite. The future of supernova studies is not just about seeing more, it is about seeing with a clarity that was once thought impossible, turning a fuzzy theoretical picture into a sharp, focused, real-time observation. From the ancient astronomers who marked new stars on parchment scrolls to the modern scientists operating detectors deep beneath the Earth, the quest to understand supernovae has always been a deeply human endeavor. It is a story of curiosity, of ingenuity, and of a relentless desire to find our place in the cosmos. We look to these dying stars not just as objects of scientific study, but as a connection to our own origins. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in the heart of a star that died in a supernova explosion long before our sun was even born. This international collaborative effort to watch the universe in real time is one of the great scientific adventures of our time. It unites thousands of people from dozens of countries, all working together towards a common goal. The prospect of one day seeing a star like Betelgeuse explode is a source of immense excitement, not just for scientists, but for all of us. It would be a shared global experience, a celestial event visible to everyone on the planet. It would be a moment of collective wonder, a powerful reminder that we all live together on a small world, adrift in a vast and dynamic universe. It would connect us, for a few brilliant weeks, to the grand cycles of cosmic birth and death that make our own existence possible. It would be a chance for a new generation to look up at the sky and feel that same sense of awe that has inspired humanity for millennia. And so, we wait. Our electronic eyes are open, our ghost traps are set, and our telescopes are ready. Deep in the quiet darkness beneath our feet and across the globe, a silent vigil is being kept. We are listening for a message from across the void, a burst of tiny, ghostly particles that will tell us one of the universe's great stories is about to unfold. We are waiting to see a star die, not as a faint echo from the past, but live as it happens. We are ready to witness the grandest spectacle in the cosmos, and in doing so, to learn more about the universe and about ourselves.